Assalamu alaikum and greetings from the Ohio State University. I'd like to thank the committee, particularly Professor Hanan and Professor Mehta, to invite me to this conference. So I'll be talking about two particular processes, and the title is Photoionization and Electron-ion Recombination of Calcium Ions for Astrophysical Modeling. These two particular processes contribute to the spectroscopy in the astrophysical plasmas or normal plasmas, and how they contribute, and particularly for calcium ions that I have chosen an example. That's what I'll be talking about today. Okay, the calcium is very important. It is found in the bones and also up to the space. So calcium is produced during supernova explosions. And then it gets scattered, and it is formed, goes to the planetary system like us. And when sun was born and calcium came, so it is in our bones, and as well it is found in the space. We know the calcium ions are found in the solar flares like this. And this is the spectrum of the sun. And in this spectrum, if you go to the left, and it is KH, those are the lines of calcium in the sun. So calcium is abundant everywhere, but we cannot see the lines of calcium in astrophysical spectrum. Until recently, we have been finding more lines in the supernova spectra. So recently we found one supernova here, right here. It's called SN 2016 HNK in a galaxy called Messier, and the spectrum shows rich calcium in a spectrum. So it is a calcium-rich supernova, and in the first peak that belongs to calcium. So it is calcium too, but we are expecting more lines or more ions to be detected as more observatories are being launched in space. Particularly, we are waiting for James Webb Space Telescope, which will be launched pretty soon, and which has a long range of wavelengths to detect. So typically, we study transitions between, among the bound levels for to observe the spectral lines. So electron and a photon can be absorbed. Electron can go to excited state, by absorption, or it can come down by emission of a photon, and from this kind of spectrum, which is the spectrum of carbon ion. So for ion is absorbing photon and getting excited, then it decays and I give out the photon, the inverse, and we get the ion back. But this photon carries out all the information. And we usually calculate two quantities for this kind of bound transitions: the transition probability or radiative decay rate, and the oscillatory strength, or the F. And if we calculate those values for large number of transitions, because an atom can be excited in finite number of levels, we can use those values to produce a theoretical spectrum. That's the way it is produced here for calcium 15. This 15, and it is over a wide wavelength range, and 7,448 transition went to make this spectrum. In this spectrum, one information we get, where the lines are very strong, and what is the wavelength region that we can choose to detect the element. So our space observatory, the telescope, can be focused to that region, or we can look at the spectrum and then we can say where the calcium 15, for example, should be available. But these are for the strong lines for bound transitions. But there are another kind of lines formed due to bound free transitions. Bound free transition means, I'm just explaining. This is the energy diagram of an atom, for example. So these are negative states until at positive state, it becomes an ion. The electron gets free. But this electron can be also excited from the ground state to various excited states. Below each excited states, there are quantum states. They are called Rydberg states. And they are particularly called auto-ionizing states. And they lie above the ionization threshold here. And these quantum states are quasi-bound. For example, a free electron coming toward this ion, and with this energy matching with one of the energy state, and this then form a quasi-bound state, and it is usually also called doubly excited state, but it is a short-lived, it breaks down and gives out the line, and which appears as a resonance, which you call a resonance in the spectrum. So for example, photoionization without resonance with like a smooth curve. But if we have this kind situation where the ion is excited, and the electron is attached to it, we can produce this kind of resonances. Actually, what is forming here, for example, this atom, the core ion can be excited here, and the outer electron can be at this energy, forming that state, and these energies are determined by these formulas. So the resonances are formed at these energies. All right. How can we obtain that or see that kind of resonance theoretically? Is to main a point lies how we describe the wave function. This is the wave function of the electron ion, and in that wave function, if we include the core ion, chi-I wave function, in various excited states, and multiply that by the interacting electron, then we get one form of wave function which is known as closed coupling wave function expansion. This kind of expansion has this advantage, is that the excited states, when used in transition matrix element, we're combining with an interference with the other state, the bound state, it can form resonance naturally. So this is the only way we can do it naturally at this time. And this is an expansion. So when you put that in the Schrodinger equation, it ends up a set of coupled equation to solve. And we can use the R matrix method to solve that set of equation. And it is then, if we get a negative energy as an eigenvalue, the corresponding wave function will be bound state. If the energy is positive, the corresponding wave function will be continuum or free state. I'd like to mention R matrix method is presently the most powerful method to study atomic processes. And my results corresponds to the calculations from R matrix method. There's a package of codes that are needed to do the calculations, and the diagram shows all the algorithm, various stages of computation. And there are 3 ways to compute, but all this computation end up giving very accurate or precise results for energy levels, oscillator strengths, photoionization cross sections, recombination cross sections, collision strengths. All these data from these processes go for astrophysical and plasma modeling. So this process, what is photoionization, is just simply ionization by absorption of a photon. So ion absorbs the photon, and we have ionization. This is the free electron. This is the direct photoionization. But if the energy of the photon is such that we can have the situation of that quasi-bound state or doubly excited state before the ionization, so photoionization, photon is absorbed, and it goes through that quasi-bound state, and before it breaking it down, then we introduce a resonance in the process, or the line in the process. So we'll see the results. It is very important to include this resonance because it is happening in nature constantly. Photoionization is a very important process. It is happening around us, where is the light source. So it is around us. But for plasmas, like astrophysical plasmas, it is the ionization is happening by a radiative source like a star, then we have to calculate the cross sections for photoionization. For such as this is the nebula or plasma where it is illuminated by the stars, and also here is the sun, and it has the corona outside photosphere. So there is ion here. The plasma is ionized by photons, so photoionization. So if we want to know the abundance and ionization fraction of any element, and here we have to use the photoionization cross section and also the electron-ion recombination rate coefficient. This shows the equation of balance. Then left side shows the ionization, like the cross section here with the flux density, and this is the ion number. And on the right side, we have recombination rate coefficient. So we can always find the ionization fraction of this ratio from this equation and and using the cross section of photoionization and electron-ion recombination. All right. So this shows the results, the photoionization spectrum. But this spectrum belongs to a simpler system. It is a lithium-like calcium. It is calcium, I think it's 18. And this spectrum shows, it carries a lot of information on these lines. So you see, these are the resonances or the lines. Okay. So at the beginning, we can see that, it is ionizing smoothly down. There is no feature. The reason is that because it is hydrogenic and the doubly excited state has not formed yet. But at these energies, the quantum state exist, and they start to form very strong resonances. These are log scale. These resonances are forming, and these resonances can be seen in the absorption spectrum, particularly in the X-ray region. So we can see another feature that at this energy, there's an enhancement in the background. The reason is that this is the excitation of the core ion to a dipole allowed state, and the N2. So that strong transition has raised this background cross section, and beyond this cross section, this is for N2 or the excited state. But beyond that, we have other excited states, but resonances are very weak, showing that resonances have been converged. So I'll show another picture or the spectrum of photoionization. These two are particular for calcium 15. This is the spectrum of two excited states. This is the low-lying excited state, and this is the high-lying excited state. So in both cases, we see resonances in this region not as strong as the region here. This is very high energy region, and all these resonances, they belong to excitation of the core to N2 complex, and they all belong to excitation of the core to N3 complex. So this high energy region was not studied in the past before the opacity project that I belong to. This was found under this project. Actually, I found it. That there are very strong resonances exist at very high energy region. Okay, these lines, they contribute considerably in the spectra. And this more prominent in the highly excited states. But in these two spectrum, we also see something, the arrows are pointing, wide resonances, like here, these wide resonances, they are called Seton resonance. These resonances appear when core itself, instead of producing that quantum state, core itself is excited and then goes down, and if the energy matches for excitation, and they are manifested as this wide area on the background. So this is for photoionization. For electron-ion recombination, this process, I'm showing it, that if there's a vacancy in the atom, for example, there's a vacancy here, a free electron moving around and find the vacancy and goes there to recombine with this ion. And so it has at this point, he has a positive energy, it recombines it to be negative energy. So there's enough energy it has to lose to combine. That energy comes out as a photon. And this photon is seen in the spectrum as a recombination line, which sometimes we call REL, recombination line. So what is happening? There's the ion exists, the electron is coming, combining with the ion and giving out the photon, which can be studied as a recombination line. But what happens, just similar to photoionization, if the energy becomes exactly matching to those quantum state, autoionizing states. So before this recombination, we can have doubly excited states, and which will introduce a line in the recombination process. So photoionization and electron-ion recombination, they are exactly inverse process. So we can study them in a similar fashion. I just like to mention one thing. When there's a direct recombination, we call it radiative recombination. When there is a resonance produced in the recombination, we call it dielectronic recombination. The recombination is also occurring in the process around us, everywhere, even in the very thin plasmas, when there is almost an empty space in space, where it is almost empty, space. So the electron still can go and combine with an ion and give out one recombination line. The emission spectrum that you see, particularly for, say, hydrogen, though those are formed because of recombination. So if we have plasma, say cold plasma, then it means that the plasma is not excited to high level to give out photons for that correspond to excited states. So how sometimes we see those lines, for example, line from this excited level coming down there and the photon, and then we consider can think of where this photon coming from. It is coming from the recombination. Electron recombines, and as the electron goes down to lower states, as cascading down, it gives us photon. So in the emission line often is created by through recombination. So this is one thing. Also, when we have a line detected from the low lines of excitation, then it depends, the intensity depends on the level population, how many levels have been populated, how many photons being emitted. But this level population also depends on the recombination, because as electrons are recombining, they are coming and populating different levels. So recombination also plays a role, and it also can give the abundances of element through its emissivity quantity. Emissivity depends on this quantity. Now the abundance of an element, which is recombined, and this is the effective rate, recombination rate coefficient. So through this equation, we can get the abundance. Also, we can get the ionization fraction using this equation of balance. It is covered right now. So on left side, we have ionization, electron impact ionization, particularly in the coronal plasma, where all these atoms are being ionized through collisions. And on the right side, we have electron-ion recombination. So solving this equation, you can also get ionization fraction. So how we can calculate, because these two processes are related, we introduced a method called unified method by Anil, Pradhan, and myself. The unified method implements the inverse nature of the two processes. The transition matrix element, which depends on the bound and free states, is the same for both photoionization and electron-ion recombination. And if we take the mod squared, we get the line strength. And from the line strength, we can calculate the recombination cross-section. Photoionization cross-section. And if we know the photoionization cross-section, we can calculate the recombination cross-section using principle of detail balance. And these are all kinematic factors. So when we have resonances in the photoionization cross-section, that means these resonances appear as dielectronic recombination in the recombination process. So in a way, we can include both radiative and dielectronic recombination, and they combined together from photoionization cross-section, and which is implemented in our method, unified method. So unified method actually subsumes both the radiative recombination and dielectronic recombination and the interference between the two processes and give the total recombination rate coefficient. This is different compared to other methods which gives it recombination rate coefficients where each part is computed separately. That means when you compute separately with different approximation, add them together, you are already introducing quite a bit of uncertainty in the total recombination rate coefficient. So for this unified method, what we do, we include recombination to infinite number of bound levels, but we divide all those levels into two groups. Group A have bound levels up to n equals to 10, and then all the levels from n10 to infinity. So we calculate cross-section, photoionization cross-sections of all these levels, and use the principle of detailed balance to get the recombination cross-sections. And for this states where the states are very close together and narrow, it is very difficult to calculate the photoionization cross-section. We use DR or dielectronic recombination theory of balanced Seton, which we extended to calculate the recombination rate coefficients. So our method provides a total recombination rate coefficient, which includes contributions from infinite number of recombined states. And also the results gives a self-consistent photoionization and recombination on cross-section, because we use the same wave function to obtain both quantities, and also it gives a total level-specific recombination rate coefficients, because it includes both RR and DR, which the other methods cannot give naturally. So this shows an example of recombination spectrum. This is particularly for calcium-15. You can see the spectrum, all these lines, they can be, they can be seen in the spectrum if given that condition, the plasma condition. And but this spectrum can be produced not exactly, but if you multiply it with the velocity of the electron, photoelectron, we can calculate the recombination rate coefficients with respect to photoelectron energy. This is the spectrum we can get, and this spectrum can be measured in the laboratories. So this is of interest because it benchmarks the methods we are implementing and the accuracy of the results we obtain. However, for astrophysical modeling, we don't use these levels. We take the temperature average rate, which will go to the model. So if we take the temperature average rate, we get recombination rate coefficient. So this figure shows the features of level-specific recombination rate coefficients. The example is calcium-15. So it's the recombination rate coefficient with temperature for the ground state and the various excited state going up to higher excited states. And you can see that the features are not similar. They depend on the temperature, and this dependence depends actually. The underlying reason is the resonance existence of more resonance will produce this kind of rise. So even though ground state is going down smoothly down, but this excited state is showing rise in recombination at this temperature, and that is because the resonances are being produced for doubly excited states. Okay, I want to show the total recombination rate coefficient where the contributions are added for all infinite number of recombined states. The red curve shows the total recombination rate coefficients that we obtained using the unified method. And this is the precise rate, I would say, because if you compare, now this is the rate, this is only for RR, radiative recombination obtained by other people, and this is the DR, so separate treatment. So you can add them together to get the total, but you cannot get the exact interference between these two processes, which is taken into account by the unified method. And the unified method had also introduced 3 small humps, and particularly the last one, which is raise the whole recombination rate to coefficient. So this is what will go for the astrophysical modeling. Not only for astrophysical modeling, these rates are needed to get the ionization fractions of in the elements that we are interested. So this is what I wanted to mention, that there are 2 additional processes, the photoionization and electron-ion recombination. They are important. Their resonances contribute to the resonances that we see in astrophysical spectra. Not only resonance, but if the resonances are not strong enough to contribute the strength of the astrophysical and spectral resonances, they dissolve in high density plasmas. They dissolve and impact the continue or the background and the shift of the shape of the background. So these 2 processes are crucial for spectral modeling, and I've just shown the features and the importance that need to be. And the example is calcium, because calcium I've been studying lately. And thank you for listening. And if there's any question, I can accept this. Thank you very much. I'll stop. Okay. I'll close this and stop sharing. And I will stop the recording. Where is the to stop the recording? Okay, here it is.